Alright, so how can we identify whether the acid in a reaction is weak or strong? Besides just knowing some of the strong and weak acids, the easiest way is to actually look at what type of arrow is in the reaction. So wherever we see a single direction arrow, that tells you that the acid is completely donating all of its H+, because all of the reactants are being converted to the product compounds on the right hand side here. So this is consistent with what we see for a strong acid. So we saw in the previous slide that HCl was a strong acid and it had a single direction arrow indicating that all the HCl was being converted into the product. Here's another example of a strong acid, HI, which is also very strong and is donating its H+ to H2O very readily. What about weak acids though? How can we detect those? Well, whenever there's a weak acid, you're going to have one of these reversible arrows where the equation, where the chemical equation actually proceeds in both directions. So some of the time, roughly 5% of the time, we'll have an H+ being given off the HF onto the H2O, and that will allow the reaction to go to the right hand side. But it's also possible that the reaction can go in the opposite direction. So this is a key difference between the two. When there's a strong acid, it's never reversible in terms of going from the products back to the reactants. So wherever you see a single direction arrow, we know that it's a strong acid involved, whereas this bidirectional arrow with an arrow pointing in each direction indicates that the acid involved in the acid-base reaction is actually a weak acid. So it goes back to the fact that the strong acid compounds are very good at being acids, giving away their H+ 100% of the time, whereas the HF is a weak acid, and therefore most of the time it actually doesn't donate its H+, around 95%, and only about 5% of the time does the HF actually behave like an acid, giving away its H+ to allow the reaction to proceed. So we have also a couple of rules that can explain the relative stabilities of our strong and weak acids. We touched on these earlier, the fact that the strong acids were very reactive and therefore wanted to become more stable, whereas the weak acids are already stable, so they're happy in the state they're in. So the first rule is basically that the strong acids are going to become weak conjugate bases by participating in a acid-base reaction. So in the example on the left-hand side here, the strong acid HI is becoming the weak conjugate base I-. And once it becomes that weak conjugate base I-, it's actually more stable. Okay? So by being converted from HI to I, it's gone from the very reactive HI to the weaker, more stable I-. So you can see that the progress of the acid-base reaction for the strong acid has actually stabilized it by converting it into that weak conjugate base. And the second rule explains what happens to the weak acid. So a weak acid will actually become a stronger conjugate base by participating in an acid-base reaction. So in the case we have on the right hand side here, the weak HF becomes the stronger conjugate base F-. So that correlates to the HF, which is stable, actually becoming the F-, which is more reactive. Still nowhere near as reactive as a strong acid, but we can say that F- is less stable than the original HF, which was more stable. So based on these rules, you can see that the stability changes through the course of the reaction. Initially for the HI, it was very reactive, but by participating in the reaction to give away its H+, it actually becomes stable. Okay, so whatever characteristic the acid has at the beginning is actually changed through the course of the reaction. So HI, being very reactive at the start, becomes the stable conjugate base, whereas on the right hand side where the acid is weak, that means it's already stable, and by participating in the forward reaction it actually becomes less stable because the conjugate base is actually stronger in terms of being able to participate in acid-base reactions more readily. So we already touched on this a little bit, but let's clarify further. So why are strong acids and bases so dangerous? Essentially, it comes back to their reactivity. They'll essentially react with whatever they can. So the strong acids will readily react to donate an H plus to become more stable, as I've shown you on the last few slides, but the bases will do the same that are really strong. They'll actually react readily, but this time they're trying to accept H plus, so they're stealing H plus from another component. So let's focus on the strong acids and see what they can actually do inside the body. So a strong acid or a base can actually destroy cells and its components, the components of the cell, say for example within the membrane or proteins that are important to that cell. And it can do this by actually forcing these components to participate in acid-base reactions. And that means they're going to lose important H+, which they need for their structures. So for example, a membrane or a protein could actually be stripped of some of its H+ within those components, which can make it more difficult for those components to function. So it's especially important that we avoid contact with strong acids and bases, really everywhere, but particularly in the eyes where it can cause permanent damage. So let's see the example here of sulfuric acid, H2SO4. So we can say it's corrosive because it essentially will break down organic material. So if it comes in contact with the skin, one of the main things that happens is the water component within the skin, the H2O, will actually be converted into conjugate acid, H3O+. So because the acid is so reactive, it's forcing the water within our skin to give away H+, and this will actually facilitate breakdown of the skin. Another interesting thing that strong acids can do is react with a strong base. So we call these neutralization reactions. And the neutralization basically means that by reacting a strong acid and a strong base together, we're creating a weaker acid and a weaker base, both of which are much more stable than the strong acid and base to begin with. So in the representation here, we've got strong acids and bases on the left-hand side, and by reacting those together, we can create components that are much more stable. So if these were both strong, then that would create a weaker conjugate base and weaker conjugate acid. And remember, whenever something has a characteristic of being strong, that basically means it's very reactive. So strong acids and bases are very reactive, whereas these weaker acids and bases that we have on this side are more stable. And it's more preferable for the compounds to be stable in this way. So what happens is the acid, of course, will donate its H+ to the base to become the conjugate acid and conjugate base. So in this particular type of neutralization reaction, the acid will actually form a salt. So you can see the formation of salt as we're pouring the acid and the base together, as shown by the white solution here. So the H+ that's on the acid on the left-hand side there is given away to the base, strong base here, which is sodium hydroxide, NaOH. And in doing so, it actually separates the two components, which are Na+ and OH-. So the H+ will combine with the OH-, so they'll come together, and the Na+ will actually come and associate with what's left of the acid. So that's why we get this salt formation, because the sodium ion that was originally on the base actually comes and associates with the conjugate base here. So the NaNO3- associates with the Na+ to form the salt, and the OH- combines with the H+ to form water. So essentially, by doing this, we've been able to neutralize both the strong acid and strong base, creating more stable components. Don't worry too much about the movement of ions within this acid-base reaction. It's actually quite complicated. what I want you to focus on from this slide is the fact that by reacting a strong acid and a strong base together, it creates weaker acid and a weaker base, and we call that a neutralization reaction. Alright, so we've got to our first participation plus question now. So make sure you have a go at trying to work through this. These questions can be really useful to confirm your understanding of what we've done, and it's a good idea to try and share these with your peers too and get ideas that you might not have considered, because often you can approach these questions in a few different ways. We've also covered the content now for questions 5 and 6, so you can access these via the revision quiz on the LMS. Alright, so for part 2, let's run through the summary. So we looked at the strength of acids and bases, and something was a strong acid when it really wanted to donate its H+. So that correlated to 100% of the strong acid compounds donating their H+ to a base. And that basically means that all strong acids, when they get the chance, will give away their H+ by reacting with a base. And we see this shown by chemical reactions that have a single direction arrow, indicating that all the reactants are converted to all the products. Whereas if the acid is weak, the weak acid is actually already stable and doesn't want to give away its H+. So only 5% of the time will the weak acid give away its H+, and in doing so it actually becomes less stable in the form of a conjugate base. So we can tell the difference here because the weak acid is involved in acid-base reactions that have a reversible arrow, with the arrow going in both directions. So we can use that as a way of picking out which are the weak acid and which ones are the strong acids. So strong acids always have a single direction arrow in their acid-base reactions, whereas the weak acids will be involved in these reversible reactions. In this section, we also had a look at our neutralization reactions, the fact that we can use the strong acid and the strong base together to actually create a conjugate acid and a conjugate base that are weaker and therefore more stable. And in the process of doing this, we also create a salt, which you can see as the formation of a white substance within the solution.